Good afternoon to all present here students. I am Dr. Rajni, Department of Computer Science, Head and Associate Professor. Today we are just going to discuss about process scheduling in operating system. So under operating system, one among the main component of the operating system is the process, and how the operating system, the operating system software is just going to maintain and as well as manage the process is what we are just going to discuss today. So under this concept, we are just going to see process scheduling, operations on process, cooperating processes, and inter-process communication we are just going to see. So the first component is process. What do we actually mean by a process? Process, we can see the process in two perspectives. The first one is a batch point of view and as well as time shared systems. So batch systems where we are just going to arrange the processes into a group of processes, and accordingly once we get a total number of processes, we are just going to dispatch them for the execution. In the case of time shared system, where the CPU is getting processed and it's been shared by different processes simultaneously, where we are just going to improve the multi-programming concept. So process specifically can be defined as a program in execution. Means that right now that particular process is holding the CPU cycle time, and no other process cannot right now demand the CPU. Once that particular process completes its task, then only it will be able to move out and leave room for the another process. So the process execution and the process progress is supposed to be done in a sequential fashion. So the sequential arrangement and as well as the organization of the processes for properly managing, getting executed, and properly we need to receive the output, we require so many things which needs to be concentrated. So all those things we are just going to see in today's discussion. So a process, specifically speaking, will be having three components basically. The first one is a program counter, second one is a stack, and the third one is a data section. Program counter is the one based on which we are just going to, the CPU will be able to execute one after the other. And the next thing is stack where we are just going to store our variables and as well as the required sequences, and data section is the one where from where the data will be fetched and the program will be using that particular data. So the next important concept what we are just going to see is process states. We have around 5 states basically. The first one is a new state. As soon as we give the process to the system, any say for example any queries, any small task we assign to our computer system is called as a process, for example, and when we assign that particular process, it will be treated as a new process. So that process is just now being created. The operating system will consider that particular process as a newly created process. And when a process is right now under execution, right now it is holding the CPU, means that that particular process in a running state. And the third concept is when a process requires some IO related activities, or else it requires some data fetching activities, in that case we call that particular process is available in the wait state. And the next state is ready state. Ready state is the one where the process stands in the queue for obtaining the CPU time. And the last state is once the process completes all the required functionalities, then that particular process will be sent out along with the output, and we call that particular process is in the terminated state. So with this diagram you will be able to understand the concept very clearly. So you are just going to, as soon as the process enters the system, it is available in the new state, and we call that, and once it moves on to the ready state, means that the process is now demanding for the CPU time. In that case that will be called as the ready state process, and we call that function as the admitted function. And from the ready state the process can either move on to the running state if there is any unforeseen circumstances. In that case only that particular process can be moved on to the terminated state. And when a process is available in the running state, means right now it is holding the CPU execution. In that case either it can move on to, once the job is over, it can move on to the terminated state, or else if it requires any IO related activity, it will be again moved on to a state called waiting state. Once the IO job is over, then obviously that particular process will be moved on to the ready state. From there it stands in the queue for demanding the CPU time. So these are all the activities running around the 5 states a process can hold. And the next very important tool, a small tool maintained for each and every process while it is getting executed in the CPU is called as process control block. The process control block is the one which holds the information about a particular process. So here I have just given a small table where I have just given the information about a single process. The pointer process state means I have just told you 5 states of process. So which state currently that particular process is available, and the pointer is nothing but the link address where that particular process or the program's coding is currently available. And the next thing is process number. We can also call it as a process ID followed by a process counter. Process counter in the sense process counter or else program counter we can say, and this is nothing but it keeps the total memory address at, from where the program starts and where the program ends, and the registers assigned to that particular process is being given over there, and the memory limits, the starting memory address and as well as the ending memory address of that particular process has been given. Apart from that, the process will be opening a number of files for its own functionalities. All those files will be listed. So these are all the details about a process will be maintained each and every time that particular process is being given to the CPU execution. When there is a possibility that the particular process halfway swapping getting out of the CPU execution and once again it's moving back when it turn comes, in that case this process control block is supposed to be updated then and there, and the CPU execution will start from where it has got left already. So this is again an important tool which is supposed to be maintained by the operating system process management component. So the next thing is this is again a diagrammatic representation of a CPU switching from process to process. So as I have just told you, it will be when you allow the processes to interchangeably getting executed, at that time only you are increasing the multi-programming concept. When you increase the multi-programming concept, then only you will be able to achieve the maximum, you will be able to maximize the CPU utilization. Any operating system's design and architecture's goal is supposed to be maximizing the CPU utilization. Means that as soon as you switch on the system till you could close the system, the CPU is supposed to be utilized fully. It is not said that 100% will be able to utilize, but still it is suggested that 80 to 90% we need to provide the job for the CPU. Then only our operating system is designed successfully. Otherwise we lack something and we need to redo or otherwise renovate our operating system so that it will be effectively uses the CPU. Okay, so this diagram if you could see over here, I have just given with an example process 0 and as well as process 1, how the CPU is getting interchanged between shifting itself from process 0 and as well as process 1. So at the initial stage, kindly understand that the process 0 is now holding the CPU time. So after a while there will be an interrupt telling due to some or other reason. It can be a priority based, or it can be a time requirement, or else some sudden requirement of a particular process to be executed. Say for example password execution, something like some prioritized process has come and this particular process is supposed to be sent out. Imagine that process 0 is now holding the CPU and right now process 1 is asking for the CPU time. In that case we require some context switch is supposed to be first made. Context switch is nothing but we need to update the process control block what we have seen earlier, and that process control block first we need to update and then we need to swap the process out. That is process 0 is supposed to be sent out and process 1 is supposed to be brought inside. So this is just going to be a like interchanging activity. It's not a single process, it's going to be n number of processes and it keeps on swapping in and out. So here if you could see here, initially when the process 0 is supposed to be sent out, we are supposed to save the state of process 0 and again we are supposed to move on to the next process, say process 1. So process 1's state is supposed to be reloaded into the memory and process 0 is supposed to be saved onto the process control block and as well as to the memory. Again once process 1 is completing its task, we are just going to move back process 0 into the main memory. Again we are just going to reload that process 0 and again save the process 1. So this will be an interchangeable activity. It's going to happen for each and every process when we achieve the multi-programming concept. So the next concept is the queues available for process scheduling. So we are just going to have different types of queues available. The first one is just going to be a job queue. Job queue is nothing but where we are just going to arrange all the incoming process for a system. And the next one is again ready queue. Ready queue is the one where we actually arrange the processes who are all asking for the CPU time, and it is mandatory that this processes who are all available in the ready queue is supposed to be arranged in the main memory or the primary memory. Then only they can demand for the CPU time. And the next one is device queues. Device queues in the sense for any IO related activity or else memory storage activity, if that particular process is asking for that device, then that particular process will be arranged in that queue. Okay, and the process will be migrating itself from one queue to another queue based on their requirement. So this is another example for shifting the processes from ready queue and various IO devices queues. And this is again a representation of the process scheduling. So here we have just considered two important concepts, ready queue and as well as IO queue. Ready queue, which is just going to arrange the processes who are all asking for the CPU time. So the processes which are all available in the ready queue will be directly sent on to the CPU. And the next queue is IO queue. The processes who are all asking for the IO, either they will be directly arranged over here or else say in the meanwhile if a process is available in the CPU and it is now under execution, suddenly it requires some IO related activity or some data from the secondary storage. Obviously it will take time, and that particular process is supposed to be sent out, and that particular process will be arranged in the IO queue. Once it completes its IO related activity, again it will be rearranged in the ready queue. And if this is one situation, and if that particular operating system is maintaining a time quantum based CPU allocation, obviously say for example if 3 cycles is been arranged for a particular process, once that 3 cycles CPU cycles is over, any process irrespective of the priority is supposed to be sent out, and the next process is supposed to be given the CPU execution time. So in that case, when the time slice is expired for a particular process, again it will be sent out. And the third thing is, if a particular process forks a child or initiates a child process, obviously the main process will be moved on to a halt state, the child process will be under execution, so the control will be moved out, and when the child process completes its task, again it will be arranged in the ready queue. Otherwise, if there is any interrupt is getting generated, obviously that based on that interrupt, the process will be swapped out of the CPU and that will be again arranged in the CPU. So you are just going to have basically 3 types of schedulers: long term scheduler, short term scheduler, and as well as medium term scheduler. So long term scheduler is the one where we are just going to arrange all the processes, we call them as jobs. So here we are just going to see a concept called degree of multi-programming, where we are just going to have number of processes present in the ready state at any point of time. So once they get arranged in the long term scheduler, again then only they will be moved on to the next scheduler called short term scheduler. From the short term scheduler only the process will be moved on to the CPU time. So here this moving of the processes from the short term scheduler to the CPU is being done by a small software module called dispatcher. So the dispatcher is a small software component which picks the process from the short term scheduler and give it to the CPU for its execution. So the next one is medium term scheduler. Medium term scheduler is the one where we are just going to arrange the processes which are already available in the ready queue being shifted to CPU, and for IO related work, if you are just going to shift the process out, then we are just going to have a scheduler called medium term scheduler who will take care of all IO related events to be completed, and then this will be moved on to the ready queue. Basically you are just going to have 3 types of schedulers. The next thing is operations on process. So to be brief, the operations on process can be creation of the processes, execution of the processes, and as well as termination of the processes. And the next concept is called a cooperating process. As I have told you, when we want to tend to have the multi-programming and maximizing the CPU utilization, obviously we will be having processes amongst themselves cooperating in the sense they will be sharing the resources, sharing the data and sharing the messages. These processes are called as cooperating processes. The processes which are all not cooperative means that they will not affect others and they will not get affected by others. They call them as independent processes. So the next concept is inter-process communications, how they are just going to communicate. So cooperating processes will be following a methodology called IPC, inter-process communication, through which they are just going to share their data and they will be able to transfer the data, and if there is any event triggered by any one of the process, that notification will be done. Apart from that, the resources, commonly used resources, will be shared among themselves, along with, say for example, global variables. When more number of processes are getting shared, we need to synchronize and we need to give a reliable data for all the processes to give their output. Okay, and the next one is how we are just going to control the processes when they are just going to get communicated and when they are just going to share so many things. Okay, so this has been done under inter-process communication. With this, I would like to conclude today's session. Thank you all.